So now let us see what's happening when you've got more than two variables and maybe more than one constraint. So definition of the problem, you're looking at an optimization problem, so written as a minimum stuff or a maximizing problem of a function of n variables, and you have a number of constraints, let's say L constraints, which are functions of those same n variables. And we have seen that we could always rewrite the constraints as being equal to 0. The next thing we do is rewrite the Lagrangian of the problem. So that's going to be a function of all your variables and as many Lagrange multipliers as you have constraints. Okay, so if I've got L constraints here, I'm going to have L Lagrange multiplier, corresponding Lagrange multiplier. Okay, so that my Lagrangian function is written as f of all your variables minus the sum on all your Lagrange multipliers times the constraint. So the difference is before is that before we only had one constraint, so we didn't have any sum, but now that we have more than one constraint, of course we're going to have more sums. We're going to have some sums, right? So next thing we have to look at is the qualification of the constraints. Okay, so meaning that we are previously, when we had only one constraint, we wanted that the gradient of my constraints was not canceling in the feasible set. And here it's going to be an equivalent condition. We have to make the matrix that contains as columns the gradients of all my constraints, and it has to be full rank. Okay, and if this matrix is full rank, then we can say that the constraint is qualified. And then the first order condition is that we can find as many Lagrange multiplier as needed, so that at the optimum value, the first order condition is satisfied, meaning that the gradient of your Lagrangian is equal to 0. So in the gradient of your Lagrangian, you have the gradient in all the x, so all the partial derivatives in x1 up to xn. So you're going to have, so I guess, no, sorry, I thought that was the next one. So you've got here, you've got n equations corresponding to each of the partial derivatives in x for I is equal to 1 to n. And here I'm going to have L equations that correspond to the constraints. Okay, so that, well, that's actually what's written here. In the end, our Lagrangian function depends on x1 up to xn, n variables that we had to start with, and L Lagrange multiplier. And in the end, we had n unknowns and L conditions. Okay, when we want to solve that, it means that we're going to have n plus L unknowns. Okay, well, n unknowns, I mean, the dimension was n, and we had these L conditions, the L G constraints that we've got. Okay, so again, let's maybe have a closer look at this. We asked for constraints qualification that the gradient, the matrix containing all the gradients of my constraints is full rank, so that they are linearly independent at the optimum point. Okay, and if ever you've got something that is unqualified, you should study them separately. Okay, and that's it. Actually, most of the time we're going to stop that and look at the values we obtain for our functions to find out whether we've got minimum, maximum, and compare them. But if we really want, we can go up to second order conditions, which are exactly the same, except that now my border, I'm meaning the border that we've got here, is exactly all the gradients of my constraints. So these are going to be L columns and L rows for that, and that's going to be an n times n square. So my matrix is really n plus l square matrix. Size n plus l square, which is what we expect because our Lagrangian has n plus l unknowns. Okay, then the result on the bordered Hessian is slightly less nice than when we had only one constraint, but it looks a lot like the Sylvester's criteria. We are looking at the principal minors, meaning the determinant when we get the full, so here the last one, so the full matrix, and when we suppress one row, one line, and so on. These are the minors, the determinants of these submatrices, and you've got this relation. If they have the same sign, so yeah, well, you've got this expression which, well, I won't ask you to use, where we will just look at maybe the bordered Hessian matrix when we have only one condition, because then it's just something that, I mean, is if you really need that, you will have something to use, some formula sheet or theorem that you can remember. Okay, so this is it actually for this part.